This equation defines the mathematical axiom of a graph. A system, G, is comprised of two distinct elements, a set of vertices, V, and a set of edges, E. Humans process these nonlinear topologies instinctively. We can look at a sprawling organic web and immediately identify the patterns of connection. Silicon has no such intuition. Computer memory is a strictly addressable linear architecture, a long sequence of cells that must be filled in order. This creates a dimensional translation problem. An engineer must determine how to take abstract, multidirectional connections and map them into the rigid, contiguous space of RAM. The mapping must be absolute. The data structure must store the vertices, the edges, and the exact topology of the network without any data loss. To bridge this gap, we use two foundational architectural frameworks, the adjacency matrix and the adjacency list. The choice between these two structures introduces a critical variable into our system design, the balance between memory used to store the network and the time required to query it. This adjacency matrix translates vertices into an n by n grid, using indices as headers. We populate using a binary rule, 1 for an active edge, 0 for no connection. We map edges AB, AC, and BC with 1s. Empty cells are filled with 0s. The structure of this grid changes based on the directionality of the data. In a directed graph, the origin and destination are strict. An entry at matrix AB does not guarantee an entry at matrix BA. But in an undirected graph, an edge implies bidirectional flow. A path from A to B is identical to the path from B to A. This bidirectionality creates a distinct mathematical property, a perfectly symmetrical matrix. If you draw an axis along the diagonal, the values on either side mirror each other exactly. This matrix perfectly captures the network's topology, but it requires the system to assign architectural weight to every potential connection, whether it exists or not. The primary advantage of this rigid grid is raw speed. It allows the algorithmic system to perform an instantaneous edge lookup across the network. To check if two nodes are connected, the algorithm simply accesses a single coordinate index. This yields a constant time complexity of theta of 1. While the search is fast, scaling this model reveals a significant hardware constraint. The memory cost is fixed. A graph with V vertices dictates a V by V matrix, resulting in a strict theta V squared space complexity. This becomes a bottleneck for sparse graphs, networks with a high number of vertices but very few actual connections. For a sparse dataset of 1,000 vertices, the theta V squared matrix allocates 1 million memory cells. Only a tiny fraction contain a 1. The rest are zeros, wasted contiguous memory representing absent connections. Using a theta V squared framework for sparse data leads to massive memory waste, necessitating a more efficient method of translation. The adjacency list acts as a highly effective spatial countermeasure to the massive theta V squared memory bottleneck we just observed. Instead of a global grid, each vertex maintains its own dynamic linked list, storing only the neighbors it is actually connected to. Reconstructing our graph, vertex A points to a memory block for B, which connects to C via a pointer. We complete the mapping by generating lists for B and C based on existing edges. This approach scales linearly. The system only uses memory for actual data, not potential connections. Mathematically, this lowers the space complexity to theta V plus E, drastically reducing the memory footprint. But this spatial efficiency comes at the cost of operational speed. Verifying an edge is no longer an instant coordinate jump. The system must perform a linear scan. To find if A is connected to B, the algorithm must traverse A's entire list until it finds the target or hits a null pointer, a search time of theta V in the worst case. The adjacency list succeeds by trading away instant edge verification to prevent a total memory collapse in large-scale systems. Comparing these architectures side by side highlights their divergent strengths. The matrix is defined by its speed. The list is defined by its efficiency. The choice between them depends entirely on the density of the network you are trying to map. An adjacency matrix is optimal for small, highly dense graphs, where nearly every node is connected to every other node. In these dense environments, the theta v-squared memory is actually being utilized, making the theta-1 lookup time a valuable asset. But for massive systems like social networks or global routing maps, the adjacency list is the undisputed standard. When you have millions of users, the number of actual connections is tiny compared to the total possible connections. These systems require O of v plus e efficiency to remain functional. This efficiency makes the adjacency list the practical foundation for executing core graph algorithms, from breadth-first search to Dijkstra's. Mastering these mappings moves us beyond static drawings and into the dynamic manipulation of network relationships, the prerequisite for analyzing any complex system in the digital world.